Today we're going to be looking at a process for how to do what's called partial fractions decomposition. Just as a sort of an introduction, think about what you would have to do when you add fractions that involve variables and whatnot. For example, say you wanted to take 1 over x plus 2 and add 2 over x minus 1. Well, what would you need to do? Well, you guys know this. You would need to make common denominators between the two. So this first fraction, we'd need to multiply by x minus 1 over x minus 1. The second fraction, we would need to multiply by x plus 2 over x plus 2. Distribute x minus 1 times 1 gets me just x minus 1. And over here, 2 times x plus 2 gives me 2 times x plus 4, distributing the 2 to both terms. And then in our denominator, we have x plus 2 times x minus 1. And then combining like terms gives us 3x plus 3 over, and if we expand the denominator, get x squared plus 2x minus x, which gives us plus x, and then minus 2. Okay. So this is how we would add fractions. What partial fractions decomposition does is it starts with this and goes to this. So we're doing this process in reverse. This winds up being a very useful process when doing certain calculus things. So if you go on to take calculus next year, you'll do this a lot. So let's take a look at how this works. So first off, in order to do partial fractions, we need the degree of our numerator to be less than the degree of the denominator. So it only works if the numerator has a lower degree than the denominator. So there are a couple, I guess, pre-steps to do that you need to think about and look at before you start doing partial fractions. One, if the degree of the numerator is greater than the degree of the denominator, then we need to do long division first. And when we do that, we'll get some quotient that's just a polynomial, and then we'll get a fraction that has a numerator with a lower degree than the denominator, and then we'll do partial fractions on that remainder. And then we need to factor the denominator. That's going to be important. So we wouldn't want to leave it like this. We would go factor it out into whatever it can factor to. Right? And then there are two more things that I'm going to put down here, but they'll make more sense after I do a bit of a demonstration, so just leave a little space there, and we'll come back to it. So let's look at an example of this. Let's go ahead and do partial. Let's find the partial fractions decomposition of that expression up here. Okay. Now, we know the answer should be this, because that's what the process is doing. So let's see where that comes from. So first, if the degree of the numerator is bigger, divide. The degree of the numerator is smaller, so we don't need to divide. Next, we factor the denominator. So, got 3x plus 3 over x plus 2 times x minus 1. Okay, and now once we have this factored, what we're doing is we want our result to be sort of in this format. Okay, and since the degree of our numerator is smaller than the degree of our denominator, when we split it up into multiple fractions, within each of those fractions, the degree of the numerator is going to be less than the degree of the denominator. And we're splitting those up into fractions where the factors of the denominator are the denominators of our two different fractions. And now we know the degree of the numerator has to be less. Well, this is a linear thing. You know, it has a first power of x. So what is a degree less than that? Well, that means there's no x, or it's x to the 0 power. So we just have a single constant value that's going to be in the numerator. And we pick a variable for that. Any variable, it's typical to use a capital A for that. Again, this is linear, so denominator, capital B. You know, doesn't matter what letters you use, but typically you go A, B, C, just walk down the line. Yeah. So we're saying this fraction can be broken up into some fraction where we have something over x plus 2 plus something over x minus 1. So that's the next sort of step. We take the linear factors and we write a over whatever plus b over our other linear factor plus c over our, and in principle we could have an infinite number, but you know, we won't go too far. We won't have too high of a degree in the denominator in our problem. Yeah, and now we want these to be equal to each other. So we have this equation where we want to solve for a and b. Okay. Now what we can do is we can multiply this whole equation through by the least common denominator to get rid of our fractions. So in this case, right here, we take all this and we're going to multiply by x plus 2 times x minus 1 to get rid of our denominators. So on the left side, what we're left with, the denominator just cancels out, we're left with 3x plus 3. On the right side, again, when we multiply through by that, this guy here, the x plus 2 cancels out, and there's an x plus 1 left, or x minus 1, sorry. And over on this fraction, we have b, x minus 1 cancels out, we're left with x plus 2. Now there are two different ways we can go about solving this and figuring out what a and b are. And I'll show you both. And you can mix and match too. Method 1 is that well, the left side, of course, just chills out. But the right side we can expand and sort of group. We have ax minus a if we distribute the first term, plus bx plus 2b, distributing the second term. And then when we combine like terms, we've got ax plus bx, so that's a plus b times x. And then for our constants, we've got a minus a plus 2b. Right. Now, if this equation is true, this equation must be true. And in order for this equation to be true, the term that has x on the right side has to be equal to the term that has x on the left side. Okay, so the linear coefficients have to be equal. So that tells us that a plus b must be equal to 3. And in order for these to be equal, the things that have no x, just the constant terms, have to be equal. So we know that minus a plus 2b must be equal to, and this happens to be 3 as well. Right. Yeah, and then we have a simple system of two equations that we can go ahead and solve. This one is nicely set up for elimination. We can just add the two equations together. We get 3b equals 6, so b equals 2, and then plugging that back in, I'll pick the first equation, a plus 2, 3, we get that a equals 1, so that leaves us, we go back to our original expression and we plug those values in. So if a is 1, we got 1 over x plus 2, b is 2, so that's plus 2 over x minus 1, and that is our partial fractions decomposition. So that's the first method. We expand this out and then collect terms and just take the coefficients on each term and set them equal to each other. There's a second method that works just as well. Sometimes it's easier. In this case, I think it is easier. Method 2, if this equation is true for every value of x, that means it is true for any value of x. So we can pick specific values. So method 2 is to plug in values for x. Method 1 is to expand and equate coefficients. So we can pick any value for x and plug it in. So if I take a convenient value, anything that makes these factors 0, that'll get rid of one of our variables that we're trying to find. So that would be handy. If I plug in x equals 1, and what happens? Well, on the right side, I have 3 times 1 plus 3, that's 6. And then on the left side, I have a times 0, that goes away, plus b times 1 plus 2, so that's 3b. And there I get b equals 2. Now what's another convenient value I could plug in? Well, whatever makes this factor 0, so that's x equals negative 2. When I plug that in, on the right side I have negative 6 plus 3, so that's negative 3. And on the right side, I take negative 2 minus 1, that gets me minus 3a plus b times negative 2 plus 2, that's b times 0, that goes away. A equals 1, and then arrive at the same answer we got using the other method. So either method works. You can just use whichever is more convenient. If your factors are all linear, plugging in values for x is going to be more convenient. This method may be more convenient when our denominator has some quadratic factors, and we'll talk about how to deal with that.